Aaron's going to talk about Stateful Serverless, which is cool because that's what Jeff already covered, so they'll probably be the same. All right, off you go.
Yep. Thanks, Lars. Who gave him a microphone? Like, who let him MC, really? I think that was a pretty terrible idea on behalf of the organisers, but we have to live with our mistakes. Hello, my name's Aaron. I'm part of the developer relations team at Microsoft. I work with Scott, who we heard from earlier. I'm a web developer by trade, which means that I tend to do stuff front end and then having to work with some kind of an API, which ends up being serverless of most recent. You'll find me on the internets at various social media points. And today I'm here to talk about Azure Functions and particularly the code-first approach to serverless in Azure, which is Azure Functions. There's actually two other forms of serverless within inside of Azure. We've heard about Cater a couple of times from different speakers already today. And there is one other form of serverless within inside of Azure, and that's the Azure Logic Apps, which is a UI-driven tool to building serverless event-based systems. But I'm going to focus on Azure Functions. And if it's your first time hearing about Azure Functions, you kind of missed some of the talks earlier today because they've already covered a lot of that sort of stuff as well. But essentially, it's event-driven based off of a whole bunch of different sorts of triggers that you can have within a system, whether they be an incoming HTTP request, whether it's an event hub or a service queue or some kind of a timer or a bunch of other things. Signaler, as Nelly talked about earlier. Now, earlier this year, I started building a project to process some IoT data that I have at home. I got solar panels on our house, so I was building a system that was going to be able to pull data out of those solar panels and then report on that within the cloud. So I start with my solar system is solar system. It's an interesting way to describe it. It's not that big. It's kind of small. It's not a full solar system. It's just a small one. But it's pulling data out. It's pushing it up into some storage inside of Azure, and it's coming up as this giant JSON payload. It's got about 50 odd properties, and I'm pulling that every 20 seconds. So I wanted to break that down into a couple of smaller data sets so I could report on it individually, because inside of this one big payload that I get, I have the data across the two groups of panels that I've got on my roof, so I can look at the power generation from them in DC, and then the AC that the inverter is converted into. I get a bunch of other metrics like the temperature, the power generation over time, and all that sort of stuff. So I have this giant serverless function that's monitoring all of that. And the problem is that I've now got a single function that is doing absolutely everything. One large monolith. Our last speakers talked about, I was building a monolith serverless, which is not really the ideal way to be building a serverless application, is it? The other problem that I was hitting is that if the data that came up was maybe a little bit corrupt from where I was expecting it to be, I had this potential of it being just corrupt for that run, and I would actually lose it because I had no way of just getting partial data out of it. I was just treating everything as one big single execution. So corruption meant I'd lose everything, which is not really ideal. Like that's a fundamental problem that I would have in my system. It would make my reporting difficult if I was losing points in time. All right, so I wanted to think about how I could treat this a little bit differently, and the idea was to use a fan-out scenario. So instead of having one single function that was going to be processing the data in its entirety, I could do that with a whole bunch of little functions. Each one would be responsible for a subset of the data. And maybe that I could integrate this with maybe a weather feed, so I could do correlation between the weather events that are happening at that point in time and the amount of power generation that I've got. In the future, I could maybe try and predict power generation. But now I have a bit of a challenge with parallel processing, because each of the functions that I've got are running independently of the other functions. They don't know about each other. They just know that they've got their little slice of the data that they've got to deal with, and they'll do what they need to do. So I'm unable to see what happens as a collection across all of the functions that are executing. So how do we know when they've all successfully completed? Or how do we know if maybe one failed and the rest didn't? I've got no sort of way of observing that in its entirety, because I have this event that fires, and then a whole bunch of little serverless functions spin up, execute, and then toddle off when they're completed. So the simplest way to achieve this in a serverless architecture is to use a queue-based chaining system. So we have our first function that executes, and then it does its little bit of processing and it drops a message in a queue. Then that queue is being subscribed to by the next step in the process. It picks it up and goes, oh, I need to do my bit of processing. It does its processing, drops its message in the queue when it's completed, so on and so forth. And all of a sudden, you've got maybe 5 of these that execute in a sequence to the end of the processing execution. And that works really well because now I can observe the entire collection. I can look at the queue along its way, and I can see what messages don't get out of it or might end up in a dead letter queue at the end. We go, well, I know that particular one failed. I can go back to the original message. I can then pull that information out, fix the problems that I might have had within it, and deal with that problem going forward. So that's not too bad. And it turns out that this is pretty much what Durable Functions does for us. So Durable Functions is an extension on top of the Azure Functions runtime. It's not an entirely separate project, or it's not an entirely separate service within inside of Azure. It's just an extension on top of the normal Azure Functions. If this is the first time you've heard about Durable Functions, they're fairly similar to step functions inside of AWS Lambdas. Conceptually, they do the same sorts of things, and we saw Jessica earlier today talking about step functions. But the implementation of them is different in the way that we do it with Azure Functions versus step functions. But conceptually, they're trying to solve the same sort of problem. What we end up with one function that is then responsible for orchestrating some sort of a workflow. That workflow might involve a bunch of children functions. Those children functions might have other children functions, and so on and so forth. But we have our overall orchestration management, which is our durable function. The durable function is capable of observing through to completion of what's happened within inside of our workflow. So I can go back and I can query the status of it. Is it in a partial complete or a fully complete status? Is it still running? What's happened with it, so I know where it's up to. It's designed for a whole bunch of different serverless scenarios. The fan-out scenario that I talked about before, that's one of its core designs. We can easily fan out a whole bunch of children and then observe them all through to completion. And that is just designed through the auto scale, and you don't actually have to do anything with that. It can also be used to implement timeout handling. So let's say that you're executing a bunch of stuff and you're waiting for some sort of external resource. Maybe you have to poll an external feed to get some data to enhance the workflow that's being executed. But if it's going to take a long time, you want some kind of notification. So you can have a timeout inside of the workflow. If I've waited for 30 seconds and I haven't got a response here, well then we can execute into another branch. We'll have a look at some of that in just a moment. Durable functions also brings a level of state management to our functions. Jeff talked about that in his keynote this morning with the durable entities and how you can get state management. And durable entities is built on top of durable functions. But what it means is that we can do things like start-stops of our serverless infrastructure. So if we are, if we're deployed into the cloud and we've got, say, a rolling update happening through, we're doing blue-green deployments, and we have our serverless application is terminated partway through workflow execution, it will actually restart and pick up where it left off. It won't start the whole thing from its head again. It will start halfway through or 2/3 of the way through or wherever it was at that point in time. This can also be useful if you're using serverless runtimes in non-cloud-based scenarios. Maybe you've deployed them into an on-prem Kubernetes infrastructure, or you're running, so the Azure Functions host can actually be deployed as a Docker container, so you can run that on something as small as like a Raspberry Pi. And if your Pi goes offline, it can pick back up at a future time and continue execution of what was already running. The support for durable functions is across both .NET and JavaScript. Sorry, excuse me. So those are the two primary languages. With the recent announcement of GA for Python support in Azure Functions, I'd expect that we might see other languages receive durable functions support in the future. But right now it's JavaScript or TypeScript and .NET in C# and F#. So let's have a look at a really basic workflow with durable functions. Okay, so I've got a workflow here where we'll start it with some form of input, and that input is going to be stored as the state against the workflows being executed. And you're going to be able to check the status of that workflow and then finally stop that workflow. This demo, the links to the code for this will be at the end of the slides. It's implemented in JavaScript, C#, and F#, so you can see how that looks across a variety of different languages. But before we execute this, we'll just have a look at the code. This is how we do the function, the entry point into this function. It's a web request function, so I will trigger it via a HTTP request. When it comes in, I unpack a little bit of input up here on line 6, just out of the URL. I'm then going to use a node module called durable functions to get a durable client. So this is the thing that's going to manage our workflow. It is our orchestrator. So I get that back from the function context. I'm then going to start a particular orchestrator with this line here, and this starts asynchronously. So basically, it triggers a background job that will then run this. Under the hood, it's actually just using Azure queues and Azure tables to manage all this state for you. So kind of like that queue chaining I was talking about, it does it all for you though. So I give it a name. I give it, if I want to control the ID of that instance that's going to be created, I can. I'm just letting it to auto-generate with the undefined there. And then finally, I'm passing in through some state as the final argument. In this case, it's just a primitive string, but it could be an object that'll serialize down for you. And then I'm just returning a 200 request to say that it started successfully. What that'll do is trigger off this workflow here. So this is our workflow function, our durable orchestrator. It's created using the durable functions orchestrator method, and this function internally, I am just extracting the input back out from the context of this function when it got started. So that's going to be that string that was passed in, or like I said, it could be a complex object. Logging it out, and then waiting for an external event to happen. So this workflow is just going to sit there and not do anything until somewhere else inside of our system triggers an event against this, the particular instance that's running and saying, called workflow, and when that happens, it'll then run through to completion. So it just kind of stops. This is just showing how a basic workflow looks. I've then got two others that we'll have a look at in due course. But let's just start this up. Actually, it's probably going to help if I run my server, because otherwise the web request is going to take a long time to time out. So let's just start that up here in VS Code. Actually, while that's starting up, we'll just have a look at the check function. So I can check the status of a durable function instance. So sorry, our workflow instance. Again, I'm doing this as a HTTP request when it comes in. I get back our durable context. From that, I can then query all of the durable workflow, all the workflows that are running, all of these orchestrators, using kind of a time scale. So I'm just saying, over the last 20 minutes, what are ones that are in any state? I can control state with this array here. I'm just saying any state instead of just looking for the ones that are running. And then finally, that's just going to return them out as a JSON payload, and we'll see that again in our demo. Okay, so let's start this up. Now that my server is running, it's actually going to execute my HTTP request. It's logging that all out, and if we zoom in over here, it'll tell us that the workflow is running. So we have something running in the background. We have a workflow that's running. I can come over here, have a look into my Azure storage account. I now have two tables, one which is the durable functions history, and one which are the durable function instances. So the instances, so these are all the instances that have been started and are running, or in various states. We can see this one in particular is in a running state. Here is the input that was passed to it. Here's the name of the parent that called it. If we have a look at the history, we can see what phases that instance has gone through. You can dig into this data. It's not particularly interesting unless you know what you're looking for. You're better off using the APIs, but it's good to know that this stuff is there. So if you have to do diagnostics, if you any sort of debugging, it's there. You can find it and you can track what's happened to something. The partition key is the ID of the particular instance that was started. So we'll jump down and let's just check the status of the workflow. If we zoom in here, because I found you can't seem to expand this particular panel without like zooming in the whole of VS Code, which is a little bit annoying. Anyway, we've got one instance in our system and one instance that matched the input that was running. That's why I've got two responses in the payload. Instance ID ends in 8A3A. It's currently in running state. Here was its input, created time, etc., etc. And just for reference sake, if that wants to expand out, come on column, doesn't want to expand out. And it's going to be really hard to read in that. That partition key actually matches, it's just collapsed and cuts off a little bit. Okay, so the final thing that we can do is we can then stop the workflow from executing, or we can trigger an event to it. Again, we do that by finding the running instance. So I do that by searching for statuses. And this is just doing it in a really primitive way of looking for a particular name and that input that was passed in. So so it'll pass in Aaron and it looks for the name workflow. If it's running there, then it finds it. And then eventually it will raise an event here against it. And that event is the same name as the event that we're looking for here. And once that's done, everything will execute. Now, the thing to be aware of, when we raise that event, it's going to drop a message into a queue that will be eventually picked up by the orchestrator that's running in the background. So it's an eventual consistency model. It's not going to happen immediately. So if you're expecting it to, as soon as you fire the event, the other one's going to immediately finish or immediately execute, there will be a potential delay. It's more obvious when you're doing it locally because it's got debuggers attached, you've only got like single processes that are executing. In a cloud environment, it's more likely to happen in near real time because it'll happen in a better scale out scenario. But it's just good to be aware that this is an eventual consistency thing. Now, while I have been using the ID of my that query string that I'm passing in, or sorry, that last parameter I'm passing in, you might want to actually get that instance ID back and track that against your user account or whatever it is that the workflow is associated to. So that's done and that should have completed. So now if we come back and check, zoom in, we'll see that the runtime status is now set to complete because that workflow has executed, because that event was triggered and everything has run through to completion. So that's how a basic workflow can be implemented with durable functions. I'll just wait for PowerPoint to start back up again. Go into dual screen mode. You can look at my lovely wallpaper. I changed it this morning. It used to be donuts. Okay, so now how does our IoT scenario look like? We've got it, our data's coming in. We still have our whole bunch of little functions, each doing their own little piece of the puzzle. But instead of triggering them by the event coming in, now we trigger a new durable orchestrator, durable function, sorry, that then manages all the children. That means I can observe the completion of all the processing of the data. I can detect when an error has happened in maybe one of my children. And if that happens, surface maybe some messages back to the IoT device or mark that message appropriately in a DLQ, or I can break into some other workflow. But now I'm able to observe the full end-to-end completion of that. So we saw a pretty basic example of workflows in that demo. But what if we wanted to build something a little bit more complex? Maybe we could go about building a game. Because if we think about a game has some stuff like player state. What's the player doing in the game? What room are they in? What inventory might they have collected? What does the game state look like? How many players are in the game? What enemies or NPCs are there in the game that the player might be wanting to interact with? What is the movement that's happening inside of the game? Is the player moving around a room? Are they interacting with anything in particular in the room? How do we have multiple users or multiple players that might be able to interact with each other? These are all things that we kind of want to think about when we're building a game, and they're the kinds of things that we can do with durable functions, because they all require a little bit of state management, and they are all things that just can happen independently of each other, but don't need to happen like as constant polling of the user. So let's have a look at another demo. This is a demo that was written by a colleague of mine. Oops, let me actually stop this server. There was a mistake I made last time, was forgetting to stop my other server. And I'm just going to start this up in the background while I talk about what it is. This is a game. It's called Durable Dungeons. It's a text-based RPG. You play as a player that goes into a dungeon. You've got to fight a baddie and collect a prize at the end of that. So we'll start this up, and you do this all through HTTP requests. So this implementation of it is in C#. I also have a JavaScript implementation of it. I was trying to get it working this morning, but I couldn't, and I figured that there was only so much time I wanted to try and write a brand new demo for a talk I was giving in that afternoon. And I spent like a good hour trying to get it to work, so I did try. Okay, so that's all up and running, and I'm just going to start a debugging console as well. I'll find my mouse, there it is. Oops. Oops, I don't need to restart that. So this one is the startup project, and let's start. This debugging console just explodes because I forgot to execute something first. We'll start a debugging console in a sec. Debugging console gives us a view into what's actually happening inside of our game. Okay, the first thing I need to do is I need to create a user who's going to be able to play the game. So I'll start that with this HTTP request. And if everything goes correctly, it should return me a 200 response. There we go, it has. Now I can start the debugging console. It has this issue where if the resources that are getting provisioned for the game to execute haven't been provisioned yet, it crashes. I fixed that in the JavaScript version. It hasn't been fixed in the C# version. If I hit the right keyboard. Okay, there we go, cool. So it might be a bit difficult to read up the back. Don't worry, what is actually written in the console is not overly important. I'll talk about the most important parts of it as we go along. Ultimately, what it's saying here is that it's going to be looking every 20 seconds into the state of the game, because this is an external application that is then just looking at that, checking what those workflows are doing, and doing that every 20 seconds. It is said that Aaron is being monitored. He's got to approve that he wants to play the game. But there's a room that's been created. There is a baddie in the room. There's some inventory in the room. So we can all get along and play the game. Now, let's play this game. And we'll start by just confirming that we do actually want to play. No, excuse me, I'm also coming off the back of the flu. Okay, so we've confirmed that we're going to play the game. It has said that the user confirmation workflow has completed successfully because I've confirmed. I've looked around. I'm standing in a smelly room with rocky walls and with faint bands of color. In the center of the room stands a dry fountain. I see a stout spear inside the room, and a shuffling red harpy is also there. And the shuffling red harpy has a 300 baud modem as the prize for me to collect. So it's obviously got a bit of Australian internet with it, so excellent. How many people are old enough to have actually owned a 300 baud modem? I know Lars used to use stone chisels to do the internet back in the day, but yeah, he's like the only one. Cool. Okay, so I need to get my weapon. Now, what did I say my weapon was called? It's a stout spear. I'm just going to copy and paste it because bugger typing. We'll pop that in here. We'll execute a request. Okay, Aaron has successfully grabbed the stout spear.
That's cheating.
What, by copy and pasting or by actually using weapons? The game gets very boring if you're not trying to use weapons because it's the only way to play. Okay, so I need to specify the weapon that I'm going to use to attack our shuffling red harpy. Let's attack them. All right, I have valiantly killed the shuffling red harpy. Yeah, I'm valiant. Don't say anything. And I've noticed that it's dropped the 300 baud modem. Excellent, I can pick up my prize and go home a happy but very slow camper. So let's grab our treasure. Go to the right tab in Postman, bang, and execute. It's not there. Oh, sorry, I copied the wrong thing, didn't I? No? Ah, stout. A stout 300 baud modem. Okay. Yeah. Okay, there we go. I've collected my treasure and I've won the game. So that's a kind of a simple example, but it's got a bunch of complex things that are happening behind the scenes. So how does that all work? Don't need that file open. We'll have a look at just one bit of the entry point of this application rather than dwell on all of it, because people are going to want their coffee shortly, and I'm the only thing standing between you and getting some more caffeine for the afternoon. And you can already see people just going in. Oh, he said coffee. He said coffee. We have our new user. So this is where we start our game. When we created our user, it comes in. It starts as a HTTP request, as we saw through Postman. It's going to unpack some information that was sent in the request. It's going to have a look to see if there is an existing user. If there is an existing user, then it's just going to error out because you can't have multiple users of the same name playing the game. If there wasn't a new user, it's going to then use the same as what we're doing in the JavaScript version. It's going to create a new orchestrator using our little orchestration client that we actually get passed in to the invocation of this function. So we're going to start a new one, and this one is called new user parallel functions, run user parallel workflow. And this is actually where the crux of how we start our new user happens. So it's in here, it comes into this entry point. So this has the durable orchestration context. So this is, again, similar to what we saw with that workflow function inside of our JavaScript example. Just, again, a little bit more complex. It gets the input, unpacks that. Again, it's just using a simple string, passing it around in this case. And from that, it's going to then create a bunch of asynchronous jobs that need to execute. Need to create a user in the state management that we have in our durable functions. We need to create their user. We need to create a monster. We need to create the room, and we need to create the inventory. Now, those four things can all happen in parallel of each other. We don't have to create the user and then the monster, and then. So we just create a bunch of asynchronous operations, execute them all, and when they're all complete, we'll then wait for the user confirmation. So this is an orchestrator that is then starting another orchestrator. So rather than waiting for an event, which our basic workflow demo was, this one's then waiting for a child orchestrator to complete. Once it's completed, it'll then flow up. This orchestrator will complete, and then that entire workflow is done. So that's how you can have a more complex scenario happening inside of a workflow, and a workflow that then uses other workflows that trickles all the way down. All right, so back to our slides. Excuse me. All right, come on, PowerPoint. There we go. Okay, so I just want to talk a little bit more about durable entities that Jeff touched on during the keynote this morning. So durable entities is an extension on top, it's the next version of durable functions. So durable functions v2 is currently in preview, and that's part of what is in that new version is the durable entities. It also has version 2 also has some abstractions around the storage, so you're not just tied to the Azure storage models. You could have something like Redis, or you could create your own. There is a preview version for using Redis as a storage model, but there are others that you could use as well if you wanted to implement the appropriate spec. Durable entities borrows heavily from the actor model, but it's not a true actor model like Akka or something like that. Don't tell the purists that it's an actor model, because it's not. But it's close enough. So if you've had some experience in that style of programming, the sort of stuff you can do with durable entities will be familiar to you. I'm not very familiar with the actor model of programming, so all I can say is it's near but not a full actor model. The other thing that it does differently to just regular durable functions is it does explicit state management instead of implicit. So where we were doing things like passing input through to our orchestrator that's then starting, that input that we're passing through is just stored by durable functions on our behalf. We don't really control that. We don't know where it goes. It just so happens to be stored. And this is fine for the stuff that we've seen in those demos where we've just used really primitive things as strings passing around. But if you've got a complex object, well, then it starts becoming a problem. Like if you've got a really big object, then you're storing a really big object, but did you need to store it in its entirety? Maybe you didn't. Or if you wanted to have multiple things that are stored against that workflow, it's actually quite difficult. Instead, the durable entities, because you have to be a lot more explicit about what gets stored in the underlying state management, it gives you a lot more power in terms of what is stored and what isn't stored. Currently, durable entities is only supports the .NET framework. I would expect that it will support JavaScript at some point in the time, given that I don't think the team wants to manage both V1 and V2 of durable functions forever, so they're probably going to want to roll forward the JavaScript version of durable functions to V2, and doing that means they need durable entities. I expect there'll be some differences in the .NET versus JavaScript implementation, because the stuff that Jeff was showing with the way that you can attribute up, or you just have these properties of types, you can't really do that in JavaScript because, types, JavaScript, what a funny notion. I say that as someone who loves JavaScript as well. All right, so to wrap up and to let everyone get out to grab some coffee or to at least stretch your legs before the afternoon sessions or the final sessions for the day, durable functions gives you a good level of state management for a lot of scenarios that we have with doing serverless programming today. It won't solve everything that you've got. If you've got really big, complex bits of data that you might want to store, then you're probably still going to want to use some sort of external thing, because at the end of the day, it is putting it into Azure storage, and that might not be the right storage model for what you've got. You might want to use a Redis cache or a MongoDB or a SQL Server or whatever it might be. But it's a great way to orchestrate workflows that are executing within inside of a system, observing them through to completion, and making sure that you're able to perform checks and balances within inside of them of what's happening. Just a couple of links. So the basic demo that I had and the blog post behind that is at aka.ms/df-workflow. And then Jeremy's Durable Dungeons demo that he had there. He's also done a Durable Entities version of it as well, so you can see and compare and contrast those two. You'll find that at the cda.ms/rq link that he's got. I'll also share out these links on Twitter afterwards. That's all I had time for today. If you've got any questions, feel free to find me around during the break. But thanks for listening.